Good morning, friends. I am here again to deliver my lecture on the course Aircraft Stability and Control. Today I am in the lecture number 38, which is pure pitching motion. In the previous class, I have discussed about the three equations of motion, which are related to the longitudinal motion of the aircraft. This relates to the motion in the x direction, the motion in the z direction, and the pitching motion in lateral axis, or it is called the pitching motion. The pitching motion is the motion when the nose is going up and down. In this regard, we have discussed in the just previous class that we have two types of modes. One is the short period mode, another is a long period mode. In short period mode, the natural frequency and the damping ratio is very high comparing to the long period or the phugoid mode. The short period maximum we consider 5 seconds. However, for the long period mode, we consider the motion for 30 to 120 seconds. In the phugoid mode, aircraft goes up and down, and the kinetic energy is converted to the potential energy, and again potential energy is converted to the kinetic energy. In this, angle of attack remains almost constant. However, the velocity u and the pitching theta will have changed tremendously. But in the short period mode, we have seen that the angle of attack variation is also taking place. However, the velocity remains constant. So, in this class, I am going to discuss about pure pitching motion in 2 degrees of freedom. Then I am going to discuss about natural frequency and damping ratios. In this case, effect of coefficient of lift and coefficient of drag in pure pitching motion. We are going to answer following questions. What is the pure pitching? How the natural frequency and damping ratio calculated in pure pitching? These questions we are going to discuss in detail in the following lecture. So, first I am going to start with 2 degrees of freedom, short period approximation. How we can solve this 2 degrees of freedom equations. To gain insight into the stability parameters and derivatives that influence the dynamic characteristics of the short period mode, we will look at a 2 degrees of freedom approximation. This is a solution in which the motion is constrained to 2 motion variables rather than 3. We have seen that in the previous that there were 3 variables. These were u, alpha and theta. But here we will only consider the 2 variables. We will make the simplifying assumption that u is a small perturbed velocity, remains near 0 or it is almost constant. So this can be removed from the equation. With these assumptions and the elimination of the x force equations, because if you make that u is equal to 0, so u dot will be 0. So we retain the z force equation and the pitching moment. So in this, the first equation which we have discussed in the previous, the first equation will be eliminated. So out of 3, only 2 equations will be there, and so we retain the first this z force equations and the pitching moment equation along with the motion of variables alpha and theta. So in this, alpha angle of attack and theta is a pitching angle. These two angles variables will be there. So if we take this, we have made this matrix in my just next class. We have, and in this, if you see the first row, this is the row, and first column, if you eliminate, only this thing will be there. Okay, so this also has gone. So only these two, and here also this two will be there. So you can see that the above equation can be transformed in this form. You can see S U1 minus Z sub alpha dot minus Z alpha, and below this minus M alpha dot S plus M alpha plus MT alpha. Here you have minus ZQ plus U1 S plus G sin theta 1, and here you will have S square minus MQS, and here US will be 0, only alpha S and theta S, and here you will have Z delta E into M delta E into delta ES. So we have assumed that the U component of this equations are 0. So equation number 1, the line which is in this matrix, the vertical, the first line is eliminated. So we have only here, and if we multiply this given equation here, this equation, then we will get the another very important parameters. Now focus on the dynamic characteristics and the characteristic equations taking short period assumptions. If we take the short period assumptions, so in this what happens? In short period is very less time. So this zeta alpha dot is equal to zeta q is equal to theta 1 is equal to mt alpha. This all will be 0. So if we put this equation in the previous equation in this, wherever these items are there, all will become 0. So now you will have a new equation matrix form SU1 minus Z alpha and minus M alpha dot S plus M alpha S square minus MQS. Here you will have minus U1S alpha S theta S Z delta E M delta E delta ES. So now if we make this characteristic equation, this you can multiply like this and like this. If you multiply, you will get the equation and make it 0. You make this determinant of this equation as a 0. So you will get SU1 minus Z alpha in one bracket, another bracket S square minus MQS minus U1S minus M alpha dot S plus M. So this arrow is from this side to this side, not this side. Okay. So this you can see that it should go from here to here. This is equal to 0. Or if we take this SU1 as a common, so you will get here S square minus MQ plus Z alpha by U1 plus M alpha dot S plus Z alpha MQ by U1 minus M alpha is equal to 0. So this here you got this equation is a quadratic equation, and this we can solve it very easily. So on simplification, we get that S square minus MQ plus Z alpha by U1 plus M alpha dot S plus Z alpha MQ by U1 minus M alpha is equal to 0. So where this M, capital M is a moment. Okay. So with variation of alpha, and here with variation of pitch. So that is the difference. For this 2 degree of freedom approximation, we can find that alpha S by delta ES and theta S by delta ES using Kramer's rule as before. So we have used the Kramer's rule here. So delta S by alpha S by delta ES is equal to Z delta ES plus M delta E U1 minus MQ Z delta E divided by U1. This equation we have put here, and same way here also we have put these equations. So how to find now natural frequency? That is also now, because by the finding out this natural frequency omega n, we can find from here that the omega n SP means short period, is equal to Z alpha MQ by U1. Okay, Z alpha MQ by U1 minus M alpha, and damping ratio zeta for short period is equal to minus MQ in this one divided by 2 omega n SP. So from here we can find out omega n and zeta SP. SP stands for the short period. So in this way we can find out that the natural frequency and the damping ratio of the system. So here now factors affecting natural frequency in short period. So what are the factors affecting? We have seen that typically minus M alpha is much larger than Z alpha MQ by U1. Okay, so this omega n SP is directly proportional to under root minus M alpha. So this M alpha, it is a moment. So here Cm alpha into Q1 as C bar by Iyy. Okay, so we can see that the following insights can be observed from equation A. For the short period mode, the natural frequency omega nsp will increase as static longitudinal stability Cm alpha increases. You see here, if the value of Cm alpha, what is the Cm alpha? Cm alpha is dCm by d alpha, and this is the static stability. Okay, so static stability is very important in the dynamic stability. That is why to have the dynamic stable, your static stability parameter has to be satisfied. So this Cm alpha is here. So this natural frequency is directly proportional to the longitudinal stability Cm alpha. As Cm alpha increases, or the distance between the CG and the aircraft AC is increasing. Okay, so this Cm alpha is depend upon the LT. Okay, LT, as it is increasing AC and the CG, your omega n SP will increase. Omega n SP will increase as dynamic pressure Q1. This you can see here. This omega n also is proportional to the Q1. Q1 is what? It is a dynamic pressure, half rho v square. So this Q1 is depend upon the velocity and the density of the atmosphere where your aircraft is flying. So omega np will increase as dynamic pressure Q1 increases, and the third, omega nsp will decrease as the pitching moment of inertia Iyy increasing. So if Iyy, it is a pitching moment of inertia. If you increase, omega n will decrease. If you increase this, omega n will decrease. So if you have more moment of inertia, your natural frequency will be decreasing. So this equation you have to remember, and you should apply this in the real scenario of the aircraft. Whenever you design, if you want that your aircraft natural frequency should be low, so Iyy it should be high, and other parameters it should be low. Okay, so like this you can. Factors affecting now damping ratio in short period. So now in the previous slide we have discussed that what are the factors affecting the omega n natural frequency. But here if you see this zeta sp is equal to minus mq plus z alpha by u1 plus m alpha dot by 2 omega n sp. Means this zeta sp is inversely proportional to omega n sp. Okay, means omega n sp, the parameter which are affecting there, like Iyy, if it is more, omega n will be less, but this damping will be high. So if you want to make the high damping, your Iyy should be high. So here mq, the pitch damping derivative, is the driving term. This mq is pitch damping derivative, is very much important. Now next one is z alpha by u1 is generally driven by other requirements, and here m alpha dot is generally driven by the same design features, that is horizontal tail size and the distance between the CG and AC of the tail and MQ, and the M alpha dot is typically about the 1/3 value of the MQ. So this M alpha dot, we can take this M alpha dot is equal to 1/3 of MQ. So this MQ and these parameters are very important. So this M alpha is dependent upon the size of the aircraft tail, the distance from CG and AC, which we have discussed earlier. It depends upon that parameters. Now 2D Fugard approximation. So we have learned till now the 2D short period mode. Now Fugard is long period mode. So for the Fugard approximation, we will assume that alpha, that is angle of attack, is constant, and with u and theta or q as the motion variable. In that, alpha and theta was the variable, but here alpha is constant and u and theta are the variable. So if the alpha is constant, and these are the matrix which we have already written, the center part, this and this and the last these equations, if you remove the remaining, if you can see here that remaining part, s minus xu minus xtu zu, and here g cos theta 1 minus z, and this us and theta s, and here mde will go, so only xde and zde will remain. So in this way, we will get the matrix like this: s minus xu minus xtu, and then g cos theta 1 in the second row, minus zu, and this minus zq plus u1 s plus g sin theta 1 us by theta s. This all we will get. And for doing the approximation, here x delta e is equal to zq is equal to theta 1 is equal to 0. So here x delta e, this one we have made the 0. Zq, this one we have made the 0. This is 0 here, and theta 1 is also 0. These three terms we have made the 0. So we will get here s minus xu minus xt. Here cos theta 0 is equal to z minus zu, and here you will get minus u1s. Only this term you will get. Here us theta s, this is 0, ze and delta e. So the characteristic equations you will get here: minus u1 s square minus xu plus xtu s minus zu by u1 g is equal to 0. This we got the characteristic equation. By this equation, we can find out the natural frequency. And how to find out this? Omega n ph is equal to under root minus zug by u1. So here minus g by u1, and zu is equal to minus q1s clu plus 2cl1. So clu is what? Clu is equal to dcl by du. Okay, and this cl1 is a dcl by at steady state condition. Okay, so here omega n Fugard, we got g q1s clu plus 2cl1 divided by u1 square m. If we assume that CLU is much less than the CL1. So as the CL1 is equal to mg by Q1S. With these assumptions, we have here omega n pH is equal to G Q1S by U1M. Here 2 mg by Q1S. This m is cancelled. Here S this is cancelled. So here 2G square by U1 square. So here this 2G and G, 2G square and UN square. So here omega n forward is equal to under root 2G square by U1 square. Very, very interesting here. So in the forward mode, omega n is equal to G by U1 under root 2. So G is constant. So omega n in forward is inversely proportional to the velocity of the aircraft. So if the velocity is high, your natural frequency will be low, and if the velocity is low, the natural frequency will be high. So in the forward mode, this pattern we have to remember. Now we have to see that what is the damping ratio in forward mode, or in the long period mode, how the damping ratio is varying. We can define the forward damping ratio as zeta pH is equal to minus XU minus XTU divided by 2 omega n. So here XU is equal to, we know that, minus CDU plus 2 CD1 Q1S by MU1, and XTU is equal to CTXU minus this. So we can substitute this value into in these equations. So we will get here zeta pH is equal to CDU plus 2 CD1 minus CTXU minus 2 CTX1 Q1S. If we assume all the thrust component 0, here this thrust component 0, so we will get, taking assumption that aircraft is gliding, there is no thrust, engine is failed. In this condition, these parameters will be 0. So you will get only CDU plus 2 CD1 divided by 2M. This you will get here. So zeta pH is equal to CDU plus 2 CDI Q1S divided by 2M U1 omega NP. So here CDU plus 2 CD1 Q1S U1 divided by 2M U1 G under root 2. Here we have put that this omega NP is equal to G under root 2 by U1. So this U1 here it will be cancelled. So here you will get that CDU plus 2 CD1, here Q1S, this U1 and this U1 is cancelled, 2 into under root 2 mg. So here CDU plus 2 CD1, 2 under root 2 into 1 by CL1. Okay, so this, how the CL1? mg is equal to weight is equal to lift. For the cruise flight, we can write mg is equal to L. So this mg is equal to CL1. So here we have put the CL1. At this point, we can make one additional assumption for low speed flight where CDU is very, very less. This part is very, very less. dCd by du is very less for the low speed flight. So with this additional assumption, we will get a very interesting parameter that this zeta damping ratio is equal to 2CD1 by 2 into under root 2 CL1. Or this 2 and 2 cancel, 1 by root 2 CD1 by CD CL1. We can also write that 1 by under root 2, 1 by CL1 by CD1. This is the ratio, L by D ratio. So the zeta, the damping ratio, is inversely proportional to the L by D ratio. So if you want that your damping ratio should be high, airplane with high value of L by D may have poor forward damping. So if you have more CL by CD, your damping will be very less. This will be very less. So understand that if you have very high L by D ratio, your damping ratio will be very low. Means if you have more CL by CD, the stability of your aircraft will be less. It will take more time to decay the oscillation, and it will take more time to come to its original position. So here I have completed my today's lecture. Hope you have understood very well. So you remember that I have covered in this very important topic of short period oscillation, then long period oscillation. In that I have discussed about the short period, your alpha variation and U and theta variation. Also we have found that in this short period mode, that omega n sp for the short period is directly proportional to the Cm alpha and Q1 and the area of your wing and tail. Also it is inversely proportional to the moment of inertia of the aircraft. We have also seen that the damping ratio for the short period is related with the MQ, that is the pitch damping ratio. Same way, if you see here that for the phugoid mode or the long period mode, the natural frequency is inversely proportional to the U1, the velocity of the aircraft, and the damping ratio is inversely proportional to the L by D ratio. So these things we have come to know, and these things I hope will be very useful for understanding the real physics of the aircraft flight, especially related to the aircraft stability and control, and how it will affect in the real dynamic stability of the aircraft. Thank you very much for joining my class. Hope in my next class I will be covering whole this topic, the aircraft stability and control. In that I will go for different other modes of the lateral and directional modes. Today I have completed the longitudinal mode. In next two classes I will complete the other, and also SAS, stability augmentation system. In the next class I am going to cover. Please tune for my next class. In that I will be covering the fly-by-wire, your conventional controls, then stability augmentation system, and so on. Thank you very much for joining the class.